Good morning, everyone. I'm Shreya Vemuganti, Assistant Professor at the University of Oklahoma. I'd like to start off by introducing my co-author and a co-speaker for this presentation, my PhD advisor, Professor Mahmood Rada Taha. He's the Distinguished Professor and also the Chair of the UNM Civil Engineering and Construction Department there. My co-presenter, Nanziri Esther Kayondo, she's an undergraduate student at the University of Oklahoma working with me on getting this work into the next stages. So what you see here is a satellite view of the Ohio disaster in 2019. This disaster is said to leak methane as much as some countries release in a year. We're looking at an internal investigation where the possibilities of failure are actually the high pressure that has caused the well's casing or the internal lining to fail. So if we look at some of the typical failure modes in wellbores, we see this particular schematic here developed in 2013. There are several stresses on cement. There's cement shrinkage inherently happening, and there's also temperature and pressure changes happening. And the typical failures that you see there, I don't know if I can point out, gap along the casing and the cement interface leads to methane leakage, cement porosity, linking up different kinds of pores in there, forming a pathway to leak the methane. Degraded casings, cracks in cement, and also the gaps along cement and formation interface. Typically, sonic and ultrasonic monitoring is used to find out the health and the environment that's happening in these wellbores. But what happens is, because of its high attenuation, cement is difficult to monitor on a regular basis. So therefore, cracks in the wellbore cement are very difficult to identify. So there is really a very high need for advanced technology in detecting cement cracking to prevent these kinds of leaks, to prevent these kinds of failures. What we're looking at and what the investigation of this particular project, the preliminary investigation, is something called phononic crystals. Now, phononic crystals are actually a combination of polymer and metal materials. Because of their high elastic constant contrast, the periodic arrangement and the surrounding matrix have these high elastic constant contrasts, which leads to a gap in the transmission spectra. It's indicated right here. If you see, there's a gap in the transmission spectra, which basically indicates the non-propagation of waves within that frequency range. It's a combination of different kinds of inclusion materials that are typically metals because of their high elastic contrast with the surrounding matrix, which is typically a polymer. So in order to extend this particular advantage, which is so famous in structural health monitoring and especially sound filtering capabilities, we looked into a very, very good material that's typically used for cement, but not in the phononic crystal aspect. Upon investigation of carbon nanotubes and how they've promoted strain sensing capabilities, piezoresistive capabilities in cement, the investigation of our literature review and several papers, even in the medical fields, had led to the understanding that actually functionalized CNTs and multi-walled carbon nanotubes have a high ultrasound capability or hyper-ecogenicity, where they have high elastic contrast and high ultrasound capabilities when they are studied with the ultrasound signal. So they have the capability of reflecting bright waves when ultrasound signal is used to look into them. So considering this aspect and also considering the properties of multi-walled carbon nanotubes, which have basically very high modulus of elasticity. We are presenting here the first kind of work, an attempt to develop cement-based phononic crystals using multi-walled carbon nanotubes. So these crystals can demonstrate the ability to control phononic waves and exhibit stop bands. These cement-based phononic crystals that we are going to present here can have direct applications in non-destructive testing and advanced structural health monitoring. So the design of this phononic crystal, cement-based, multi-walled carbon nanotube-based crystal, started off with a multi-physics simulation and design and modeling of finding out what exactly is the geometry of this crystal. Because geometry, material properties, and the filling fraction, which is basically how much of this matrix is filled with this inclusion, is what affects the band gap or the range of frequencies in which there is a band gap. So upon design, we developed this particular design where you have an inclusion of 3 millimeter diameter in a unit cell of 4 millimeter. We've observed 3 band gaps, narrow full band gaps, but some of them are very wide band gaps in partial stages. So now the idea of developing this and fabricating this is very challenging because you're looking at nanoparticles essentially becoming pores in a cement matrix. Biggest challenges, how do you develop cement matrix with these small holes? It's a brittle material. So after much investigation, we came up with a great technique using 3D printing, which I will be discussing in the future slides. This is the fabrication for the nanomaterial densely packed core inside the cement. We used MMA as the resin in which nanotubes would be dispersed. We used a solvent which has very high evaporation rate. It's dichloromethane. The carbon nanotubes used were multi-walled carbon nanotubes, functionalized based on the medical paper that we investigated. And we used a hardener for the MMA to make a solidified mixture of the core. Calendaring process was used because based on prior literature and investigations, it was found out that calendaring can have the ability, instead of the ultrasonication and the typical mechanical steering we do for carbon nanotubes, 3-roll milling or calendar milling is a process that has shown to be successful with higher quantities of carbon nanotubes. So we use this process, a mixing protocol was developed based on literature, and this yielded a nice homogeneous mix that we will use. So after the 3 passes, you see these nice roll-ups of the carbon nanotube particles that were then used to fill into the cement. So coming to the cement and how a core, a matrix of cement with different kinds of these holes to form that periodic lattice, we used a inverse mask printing process, which basically says that instead of using a mold to cast the cement, we used a mold that would make holes in the cement. So we 3D printed this wax mask and we impregnated it into oil well cement base. And these holes, after many, many trials, were very successful in identifying that the entire wax evaporated from it through heating process, and we had clear spaces for these inclusions to be deposited. So micropipetting technique was used with the carbon nanotube mix that we formed to get into these inclusion spaces. And eventually, after several fills, we had a nice compact fill into these inclusion spaces. To understand what kind of context we're looking at, we studied 5 of these pores with thermogravimetric analysis, and we had a good, after good statistical significance, we saw about 77% of this synthetic inclusion mix into these pores. So we have the cementitious matrix with these inclusions for acoustic band gap capabilities and for ultrasound without having any plate mode effects or interferences. of the ultrasound, we needed to make sure that there is less number of pores or less number of interferences that affect this ultrasound. So after conducting ultrasound for just plain cement, we got this lambda distance that the sensor needs to be placed from the transducer that's actually getting the ultrasound. So we developed this particular setup to minimize the pores inside the structure. We had 3 types of specimens. Specimen A denoting that particular specimen which had the sensor inside. Specimens B and C indicating really just a homogeneous cementitious mix. But specimen C's speciality is that we had a plain cement slab inside this entire specimen in order to understand whether we are seeing whatever result we're seeing after the acoustic testing. It's not just because of a presence of a slab, but actually because of the presence of these inclusions and the matrix contrast. So first, after the acoustic testing and everything in that process, we constructed X-ray tomographic reconstructions. Specimens B and C, which were basically the homogeneous mixes. We saw the presence of that slab in specimen C. So as expected, the results, we saw cementitious mixture homogeneous. When we came to the one with the sensor that our study was focused on, we saw this nice difference in densities, a clear representation that the cement and the carbon nanotubes were different materials. Looking more closely, we saw that there was an interfacial debonding with the CNTs for the cement because of the cement shrinkage, and we wanted to study what kind of effect with the band gap as well as this particular interface debonding is creating in our results. So just looking at the acoustic testing for firstly, specimen A, which had the cementitious acoustic band gap sensor, demonstrated 2 band gaps at 300 and 600 kilohertz. Specimens B and C, which did not have the cementitious acoustic band gap sensor, did not demonstrate band gaps. Very important to note that that second feature in the specimen A, which is a representation of that changed wave propagation. So like I mentioned in the interfacial debonding, we have the results, we had the band gaps, we know that our work is, we were successful in that proof of concept. But because of that interfacial debonding, we wanted to make sure what exactly is the effect of that interfacial debonding. Is it changing the band gap frequencies? Is it amplifying some of the band gap frequencies? So that was very important for our investigation. So we made a COMSOL 3D model, and we had different cases representing the specimens B and C, which were homogeneous, but also representing specimen A with the sensor, but specimen A with the interface debonding. So these 2 different modes were very important to understand. So specimen A, which is basically a healthy cementitious sensor. There was no interface debonding. If you look at that, that's our typical band gap structure that we saw. And that's the amplified frequencies where there was band gap that actually was present. But because of this interfacial debonding, which is basically model 3, an interface of air layer was modeled, we saw there were differences. There were differences in basically amplification of that frequency of the band gap. So plotting one over the other, we saw that model 2 and model 3 had the range of band gaps that we designed the sensor to have, but some frequencies, especially that 300 kilohertz and that 600 kilohertz, which were identified in the acoustic testing, were amplified in the one that had the interfacial debonding. So some of the key takeaways from this particular investigation was, of course, the periodicity characteristics of the NWCAT's inclusions in the cement sensor, mismatch between the inclusions as well as the matrix. That was the result, and that was the result of the band gaps that we saw. The 77% synthetic inclusion mix was a challenging task to achieve because carbon nanotubes are high surface area nanoparticles. So that was produced using dichloromethane as the solvent because it has a very high evaporation rate. Experimental testing of lab fabricated specimens confirmed that there is a band gap between the 300 kilohertz and the 600 kilohertz, more amplifying that particular frequency there above and below the 500 kilohertz range. X-ray tomographic reconstruction showed there was an interfacial debonding, but we confirmed with the modeling that microscopic debonding is resulting in a shift of frequency of minimum transmission, but the band gap was not perturbed or disturbed in any way. So this is our paper published last year in Smart Materials and Structures. For more detailed information, if you would like to look into the calendaring process in more detail, the protocols we followed. This is our patent that was filed successfully last year. We had the provisional a while ago, and we successfully had the filing in lab the year before. I want to acknowledge especially Dr. Thomas Duers from Sandia National Labs, Professor Laura Parak-Nolte from Purdue University, who had the acoustic testing for us, and Dr. John Stormont at the University of New Mexico. For the ongoing work, I'd like to invite my undergraduate student, Nanziri Esther, who this is her first ACI, and I welcome her on behalf of all of you. Yeah.
So the work we're doing right now is really focusing on how can we optimize this band gap, but also what are the things that are going to affect the band gap? So what's going to cause a shift in the band gap? What's going to cause the band gap to be narrower or wider than we expected it to be? Bandgap optimization really just means that we want there to be a bigger band gap. So we want a wider range of frequencies for which there is no wave transmission. And if we have this, then that would improve the quality of our work because we have a wider range of frequencies to work with in order to predict how the sensor will behave in certain conditions. And there's both internal and external factors that will have an effect on this band gap. One of them, as you can see on the right, is the location of the core material. So if you take out some rows of the core material, you see that the direction of wave transmission changes, and that will in turn have an effect on what the band gap expected is. The other internal effect is the filling fraction. So how much of the matrix is surrounded with the core material is important to determining what this band gap is. In order to study this, we took a constant outer matrix of 4 millimeters by 4 millimeters, and we changed the diameter of the inner core material to see how that would affect the band gap. So on the left, you can see that with 3 millimeters diameter, we have 3 band gaps, which are much wider. And then with a 2 millimeter diameter, we have a smaller band gap and just 1. And then with 1 millimeter, we don't have any band gaps. So we see that it's important to take into account how much of the core material relative to the surrounding matrix. So for external factors, we have things like pressure also affecting the band gap expected. So at the top, you can see that we did a simulation with a frequency within the band gap range. And that center part with the circular things is really the sensor. So you see that the waves are being blocked by the sensor within the band gap range. However, at the bottom, when pressure is applied, we see that the waves are being transmitted, which means that when there's pressure being applied on this sensor, on the cement, then there's going to be a shift in the band gap. The other external effect is defects. So what happens if the surrounding cement is damaged? What happens if there are cracks, if there are things like those things that we want to sense with this sensor? So on the left, we took a simulation out of the band gap range. Again, the center is the sensor. So we see that the waves are being fully transmitted. However, on the right, we see that when the surrounding cement is damaged, so when there are holes or cracks in the cement, then we see a band gap where we did not expect a band gap. So this is at the same frequency. However, the waves are not being transmitted through because of the defects. So we want to understand what are these internal and external factors, how do they affect our band gap, and how can we be able to predict what the sensor will behave like and determine what the signature of the sensor would be.
So to end this presentation, I'd like to thank, of course, my PhD advisor, without whom I wouldn't be standing here today, Professor Mahmudra Dattaha. I'd like to acknowledge some of the funding agencies that are right now a part of my process of assistant professor in the journey. The VPRP office at OU, the Alva Center Women in STEM, who have generously funded one of our projects. Transco Industries with their generous donations of materials. And this is currently our group with a student coming in fall 2022 for his PhD. And we are the Immerse Lab, and I'll be happy to answer any questions. Thank you.
Excellent presentation for both speakers.